And the GPU slides, I was not there. There was no preparation for the GPU slides, so I will show you the GPU part directly from the documentation. So the GPUs. So let me go in the documentation to the guides per supercomputer, Setonics guide, Setonics user guide. Come on. Running jobs on Setonics. By the way, here are examples, more examples of batch scripts, a bit more elaborated than the examples in the slides. And here are examples for running batch scripts on the GPU nodes. So this part of the documentation is a bit complex and long, but yeah, you need to read that carefully. So the first thing to notice in the GPU nodes is that we have 4 cards. Each of the cards has 2 GCDs, which in this slide we are calling the GCDs as GPUs. So basically in the documentation, if you see GPU or GCD, they are equivalent most of the time, except for example here we have 4 and 5 to 50 GPU cards, but at least we are saying that these are the GPU cards. And we are basically explaining that it has 2 GCDs, and we are going to do the equivalency of GCDs and GPUs. Because for Slurm, this is a GPU. That's how Slurm sees it. So these are in this schematic, these are the 4 cards, each card with 2 GPUs. And this is the single chip that is managing the node. So each of is a chip with only 64 cores, only 1 chip in the GPU nodes. And as from previous schematics, you may remember that the total 64 chip is organized in chiplets with 8 cores each of them. So what is important here is that now really the chiplets makes more sense in the way that each of the chiplets is connected directly via this fast connection that is called well, I forgot the name of the AMD technology, but I guess it's an InfiniBand AMD fast technology. It should be somewhere in the documentation, but anyway. Each of these chiplets is connected directly to 1 GPU. What is a bit funny is that chiplet 0 is connected to GPU 4, while chiplet 6 is the one that is connected to GPU 0. Why is that? Nobody knows, but that's the way they organize this. This is important because if you want to run optimal code, you want the CPU cores that are dealing with GPU 4 to be in this chiplet. So you don't want that C32 sending data towards GPU 4. So it is to reach GPU 4, data should go through GPU 6 and then go through this connection channel and reach GPU 4. So it will take 2 jumps to reach GPU 4. So it's better to have a CPU core directly connected to GPU 4 dealing with it. So that's the main problem we have with the GPUs and the difference in the way we are using the Slurm commands. What else? I think that's the most important thing to notice. So this diagram is very useful for you to do your checking to see if the assignment of resources is correct for you. Now, to using the GPU nodes, you need to specify your account. So the -- account is the same as -- A. And then if you remember, then we put the name of the project. But in this case, to be able to use the GPU nodes, you need to put the name of your project -GPU. That's the way we need that. So that's the first difference with the CPU scripts that we saw a few minutes ago. You need to add that suffix in your project name. The second difference is that for the allocation of resources, you don't need to specify all these combinations of settings. So we simplify this towards just 2 settings. So this is the only thing you need to query for resources to Slurm in the GPU nodes. You need to query how many nodes or in how many nodes you are going to run and how many GPUs you are going to use. That's it. So you don't ask for memory, you don't ask for the number of tasks, you don't ask for anything else. So what we did, and this is an internal setting just for Pawsey, so you will not find this anywhere else or in the Slurm documentation. So this is a setting for us to make things work properly. And I think it's very easy. So the only confusion may come that you will not find this documentation anywhere else. So it's just like a Pawsey only thing, but it's very easy to understand. So what you are asking is for what we are calling allocation packs for the GPU nodes. So for example, in this case, 1 GPU means you get 1 allocation pack. And that allocation pack contains 1 GPU, 8 CPU cores, or 1 chiplet, and the proportional amount of memory for 1 GPU. It's 1/8 of the total memory in the node. That's the memory you get. And for example, in this other line where we are asking 1 node and 3 GPUs, you get 3 allocation packs. So basically the GPUs per node is equivalent to the number of allocation packs you are asking for. And when you ask for 3 allocation packs, you get 3 GPUs, you get 24 CPU cores, that means 3 chiplets, and you get the equivalent amount of memory. It can be that you get this chiplet and this GPU, then this chiplet and this GPU, and this chiplet and this GPU. That can be. But what we are doing internally in our own settings for Slurm is that the allocation packs are assigned like 1/1. What I mean is if you get chiplet 2, you get GPU 2, and if you get chiplet 4, you get GPU 6. There is still one additional thing you need to do for have the optimal binding, but at least those are the GPUs and the chiplets you are getting. Now, when you go to the second part, so this is the allocation, and this is the resources that you get. But then you go to your script and reach the line for the srun. In the srun, for these 3 GPUs, you need to tell, okay, I'm running in 1 node. I'm going to use 3 tasks. I'm going to use 8 CPUs per task. Remember, this is not telling that the code is going to use those OpenMP threads. This is telling that the resources are going to be held by this job step as indicated. So this number 8 comes from the chiplets. So basically we are saying, okay, just for this job step, basically block the whole chiplet and don't allow anyone else to come into that chiplet. So that's why we are using the number 8 here. Then we are saying we're going to use 3 GPUs per node and only 1 GPU per task. But additionally, when you do this, you are still not telling Slurm which GPU is going to be connected to each chiplet. So basically, if you got 3 chiplets, like let's say 0, 3, and 5, and you got then GPU 4, 3, and 7, if you execute the srun without this final indication of GPU bind closest, then you maybe have the core 40 sending data and running its stuff in GPU 3 and probably core 30 running stuff and sending data to GPU 7. So basically the way you guarantee that GPU 3 is dealing with chiplet 3 and GPU 7 with chiplet 5 and GPU 4 with chiplet 0 is this last step, GPU bind equal closest. So that's the final indication for the GPUs. So I know this is sort of especially the way you are asking for resources is just Pawsey specific. This not. This is general Slurm, but that's the way we're dealing with the resources. So then what we have here is some other examples where the match is not exact. So for example, if for some reason you need 1 GPU or 1 GCD, but also you need to do some things in the CPU in 14 OpenMP threads, this is not like exact match. So 14 OpenMP threads in the CPU, you will need 2 chiplets by force because each chiplet has 8. So basically, because you cannot ask for exactly the resources you need to ask all them via allocation packs. The allocation pack that covers your needs is 2 allocation packs, and to get 2 allocation packs will give you 2 GPUs and will give you 16 CPUs, which cover your needs. Then you need to ask for these 2, and you ask for them via the GPUs per node too. Once you get your resources, then you use them differently. You use them as you wish originally. So the OpenMP threads is controlled by the variable of OpenMP num threads equal 14. And then in the step, you say, okay, I'm running in 1 node. I'm running 1 task. I'm allocating for this job step the 16 cores of the 2 chiplets, although only 14 will be used. That is controlled by the OpenMP by the OpenMP environment variable. Then you only wanted 1 GPU, so then you say only 1 GPU, and GPU per task only 1. And that's it. So in the srun is the place where you restrict to the exact amount of resources you need. What else for the GPUs? Yeah, okay. So in the documentation, there is this test code that is named hello job step. So I guess we can try to use it. So let me do the demo that comes here. You can you can practice that yourselves, starting from here. But I will do it. I will do it now. So cd my scratch. I was already there. And then the hello job step. The hello job step code is in this repository. So let's clone it. Git clone GitHub hello job step. So I will post this in the chat. So that's a place where the test code is. So then, after cloning, I go to the hello job step directory. And to compile it, I need to do it in a GPU node. That's the best place to compile GPU code. So the login nodes are not do not have the GPU architecture. So it's better to go into a GPU node. So for that, we can do SLOC for activating an interactive session. So SLOC, and then I'm going to use the reservation that we have for this training. So you use -- reservation equals, what's the name of the reservation? So if we do reservation summer internship 2023, and then we need to tell the account to be courses 01, that's the project for the training, and then GPU. And then I'm going to tell I'm going to use only one node and GPUs per node equal 1. Okay. I need to say my partition is the GPU partition. Okay. Okay. Let me see if there is space available in the GPU development partition. There are 4 GPUs, 4 nodes idle. So I'm going to SLOC there. SLOC partition GPU development account courses 01 dash GPU, one node and GPUs per node equal 1. Okay. So remember, if you're doing an SLOC towards a GPU partition, you only need to specify the number of nodes and the number of GPUs, because in this case, we're only asking for a GPU pack. In this case, yeah, only one GPU. And that GPU pack will give me 8 CPU cores and the corresponding amount of memory. Okay, so after cloning, you need to load the Cray programming environment. You need to load this module that has all the libraries for the GPUs, and also the ROCm module that has also libraries and for the GPUs. So we need to load all these. So let's module load Cray programming environment, and the two modules related to the GPUs. So once we load that, we can compile the code. So we just do make hello job step, and that will compile the code. So this test code basically just checks what is available on the resources and what can be assigned to each of an MPI tasks. For example, this is an example using 3 tasks, and if you run it like this and it's run without the additional parameters that I told in the top table, what you will see is that for task 0 is able to see the 3 GPUs. And that is something we normally don't like. So we like one of the tasks only seeing one of the GPUs and communicating with one of them. So here in the example of the documentation, when you say 1 GPU per task and using bind equal closest, what happens is that task 0, for example, is only seeing 1 GPU that you can identify with the boss ID. So in this case, the MPI task 0 is in the core number 2, and that core number 2 is seeing only the boss ID D1. So if you go to the top map of the GPU node, D1, and it was the core O2, is related or directly in communication with D1. And if you check the 3 of them, you will see that communication is now direct. Yeah, here. And that is all because you are doing the GPU bind equal closest. So again, this MPI task number 2 is running in the hardware core number 17, and that is one is using the GPU C9. So again, number 17 should be here, is in chiplet 2, and that one is in direct communication with C9. So that's the idea. So we can, so hello job step is already here. So if we do srun 1, then I only ask for 1 GPU, so I only 1 task, but these are the parameters I should use. So 1 node, then GPUs. So I'm being very explicit. GPUs per node equal 1. GPUs per task equal 1. And GPU bind equal closest. and then hello job step. I forgot to set the OpenMP environment variable. So if I do export OpenMP num threads equal 1, and then ds run. Okay, so only one thread. The GPU, the task 0 is running in the CPU 10 and is using the D6 GPU. So let's see. Number 10 is using the D6, so that's okay. And for the case when I was not setting the number of threads in the OpenMP part of the code, then it was using 8 OpenMP threads. So basically, MPI task is 0. The thread can be 0, 1, 2, 3, 4, 5, 7. These ones are running in these CPU threads of the GPU chiplet, which is the chiplet corresponding to what we saw in the map, and all of them are seeing GPU D6, which is the corresponding GPU connected to that chiplet. Okay, so I guess that's it for the GPU part. There is a lot more for you to read here. And we also have examples of how to run an exclusive node example, many nodes in exclusive, or a single GPU, or in 3 GPUs in a shared node. Also in this documentation, there is a second way of getting the right binding of the CPUs and the GPUs. That is called the manual optimal binding in the documentation. That is because some codes may still complain with these settings. So especially those that are using OpenMP or OpenACC to offload to the GPU, they may complain and they may not work properly. But there is another option, which is a bit more complicated, and I'm not explaining today, to generate that binding. What I will say just now is that for that option, you need to use this generate CPU bind script that is available to all the users, and do some kind of receiving information from that script using an additional auxiliary script that we call a wrapper. And with these two settings that we are calling the auxiliary techniques. What is happening here? First auxiliary technique is the use of the wrapper. Second auxiliary technique is the use of the generate CPU bind. And then you use those here in the srun. Again, I'm not explaining it right now, but it is, I think, well explained in the documentation. Just in case if your code is suffering with this first approach of binding, you can try the second approach of binding. Yeah, okay. So I think that will cover the how to run on the GPUs. Do you have questions? So the chiplets are parts of a single chip. So like a multi-core, this is a multi-core chip. So this all together is an AMD chip. So that's the CPU, if we can say it, all together. So this chiplet thing is a division of the of that CPU. So we have also in the documentation this diagram of what is the chip, the representation of the Zen 3 CPU. So that's the chip. But this little organization, inside the chip is called chiplet. That but these all 64 blue squares are the 64 cores in a chip. But this is just the way it is organized.
But this organization is different to the GPU chip.
Yeah. Yeah, exactly. So they are two separated things. So this, in the case of the CPU nodes, we have two of these, and adding up to 128 cores, 128 of these blue squares in a single node. In the case of the GPUs, we only have one of these, but the CPU is really more not used for computing, but for controlling the node. And that is this. This is a single CPU. Then we have 4 cards that are physically 4 separated cards. These are the MI250s. So these are physically 4 different cards connected in the node. But there, the way the AMD created all the cards together was, okay, there is a direct connection, fast communication between one piece of the chip, one piece of the GPU. This piece is the chiplet. Direct communication of this chiplet of all these cores with this GPU, and direct communication of all these cores that are in the CPU directly communicating to the GPU. Inside the GPU, there are many, many cores to do the computation. So we are not seeing here any kind of architecture of the GPU. So this is a black, well, not a black box, this is just a white box, but here is a very intricate architecture that does computation in a super fast manner.